to the PowerPoint that we just had here. And right now you should all be seeing this. And what I'm going to do is I'm going to just do a brief review of what we covered last class period with Caroline doing the honors here. I'm hoping here that all you guys see right now. Caroline, can you verify everyone can see the chapter 9 chemical reactions from my screen?
Yeah, they can.
Okay, so let me remind you of a couple things. I'm just going to I'll go into slide mode and I'll go kind of quickly through this. If you're wondering, you have this PowerPoint is in your notes, but just you're aware, reactions we're doing, they come with two parts. They have both the reactants and the products. Reactants are on the left-hand side. Products are what you end up with. Can you guys see my little mouse as I move through here, Caroline, or no? I'm circling reactants. Yes. Can you guys see that? Caroline, can you see that?
Yes.
Okay. So reactants go to products. I'm not going to spend any more time with that because that's just straightforward stuff. In a chemical reaction, the way atoms, these are all things that are reminders of what we did before. And I think you might have done this with Mr. Braidaway, so I'm not going to spend any time with this. But essentially, that's just showing you how word equations can then be transferred into oops. Oh, by the way, this is kind of a big deal. If you ever see S, G, or L after a compound, that means that we're dealing with a solid, a gas, or a liquid. And anytime you see an arrow, the arrow means reacts or yields to form something else. This, again, is stuff that you should have covered before. Aqueous means dissolved in water. A lot of things happen when they're dissolved in water. Double arrows means that we have a reversible reaction. Again, I'm going really, really fast this because I'm assuming one that was already covered with Mr. Braidaway, but two, you can look back through this afterwards. I want to get to where we were actually. I'm just going to run through this here. Okay, by the way, the very bottom of the page, ionic compounds were required to consider the charges in order to write the formulas. That's what we just did this morning. So what we did this morning is we had you guys do a crossover between the metal ion and the positive ion. If you take a look here, sodium is a good example. Sodium is a +1 and oxide is at -2. So that 2 is going to cross over down below the Na, and the 1's going to cross over down by the O, and you end up with N2O. And if you ever have a covalent compound, which, how do we know we have a covalent compound? Anyone want to unmute and jump in? How do we know we have covalent compounds? Ionic compounds are a metal and a non-metal. What are covalent compounds? Anyone? I'm only looking at the PowerPoint, so this is kind of depressing. I'm hoping you guys all haven't left the screen, but so I'll just keep on teaching because we can document via video how terrible I am. Whenever you have two nonmetals together, so if you see the zigzag line on the periodic table, anything up to the right-hand side, those are nonmetals. So if you have ever two or more of those together, like, for example, CO2, then we have to name them using prefixes, carbon dioxide. Or if you had like N2O5, you would say dinitrogen pentoxide. So that's stuff that we did from before. And I reminded you last class period, maybe I didn't, of diatomic molecules. So Brinkelhoff, Caroline, I can't remember what we did last class period, but in my notes, I talked about some elements that always are, let me escape out of this real quick. And I'm gonna go back to my screen here. Okay, Caroline, can you go to the board really quickly? Or can you write on the board really quickly? Can you unmute yourself? You're still muted. Caroline, can you unmute, please? Okay, so there are some elements that when they're by themselves, you always have to write them as pairs. So I want you to write Brinkelhoff, BR, it's on the board, right? BR, I, N,
Wait. Oh.
BR, I, N, CL, H, O, and F. Okay, So that's an acronym. So underneath the BR, I want you to put a 2. And underneath the next to each of those letters, I want you to put a 2. I2, N2, CL2, H2, O2, and F2. So what that means, if you have any of those that are part of your equation, you always have to write them as 2. So, example, do an example. Can you write underneath? Can you write sodium plus oxygen?
I don't even. What does letters mean?
I realize I'm not broadcasting on your screen, so they're just looking at me right now. Are they broadcasting on your screen? Oh yeah, we are. So watch. Let's just do a quick recap of what we did last class period. So isn't that the puppet show of one thing with one thing? Can you show me the puppet show with 2 fingers held up? Okay, go ahead. Just keep them. Yeah, you're absolutely right. But just hold them by yourself. Good, perfect. So anytime you see a single thing and a single thing, that's going to be a synthesis reaction, and they're going to hook up together to form one compound. So go back up to the board here. Go back up behind you. So if I have sodium plus oxygen, they're going to hook up. They're going to form on the other side sodium oxide. You put an arrow and write the word sodium oxide.
No, sorry. It's okay.
Now, watch. And this is what I was just telling you here. When we try and write the equation for this, sodium is going to be Na, so write Na. Plus oxygen, but isn't oxygen part of Brinkelhoff?
Mm-hmm.
Up above? So when we write oxygen, we can't write plus O, we have to write plus O2. Can I get a thumbs up from everyone here if that makes sense? So from here on out, whenever you have any of those 7 things right there, you put it as a pair. Now I'm not going to follow up the rest of this problem, but this is stuff that we did yesterday for work. So I'm going to jump back to screen sharing here. Caroline, you can keep unmuted. That way, if I have any questions, you can respond on behalf of the whole class. So I'm going to go back to myself here just so it's not presenting off of yours. And we're going to go to this. Okay, so that's where we're at here on this in the set at the very bottom. If you have Brinkelhoff, any of these right here in an equation, they're going to be written as pairs. Hopefully that makes sense. Now, this is all stuff that you guys probably did with they asked you to go from the word equation to the formula equation. This is stuff that you did with Mr. Braidaway. I'm not going to do that with you again. And these are the answers for those, so we're just going to rip really quickly through them. Balancing equations. We talked, again, you talked about that with Mr. Braidaway. Balancing equations, the big thing is the number of atoms you have on one side have to be equal to the number of atoms you have on the other side of the same kind. And the way we balance is by using coefficients when we need to. I'm going to rip through this here because this is stuff that should have been covered before. The cool thing about this is that this PowerPoint is sitting in your shared folder, so you can look through these notes at your leisure afterwards. And so I'm just going to run through all of this right now. These are just examples of balancing. For those of you that are watching online for the first time, I'm really sorry. So let's go to types of reactions. This is where we started last time. There's going to be 5 different types of reactions. Focus on the 3rd bullet point there, and you'll be able to predict the products from what template we have. This is our puppet show. Now, so this reaction, you have 2 elements or compounds combined to make one compound product. So for example, here you have Ca plus O2, and if you're thinking in your minds, what does that look like? It's like the puppet show that Caroline just did. 1 finger and 1 finger, and we put them together. Now notice, see how the CaO on the right-hand side does not look like it's balanced with the formula on the left-hand side? That's because when you're writing the products on the right-hand side, you're writing a balanced ionic formula. It is independent of what you did on the reactant side. Now, this is not a balanced equation, but that's where we put coefficients in to help us out. In all these cases right here, these are examples of how we can put together 2 elements or 2 compounds to form one thing. Now, I've been focusing on two elements, so we're going to stay with that right now. Okay, so just for fun, I want all you guys right now on your paper to write for me what the overall balanced equation would be for that. Do this on your own, please. Really quickly, write what the formula down. This PowerPoint is skipping the word equation, so I want you to just write what the formula would be. Now, real quick, let me remind you, calcium's a 2+, and chloride's a Cl-. So it's kind of a big deal that you don't look at what's on the left-hand side and just write it on the right-hand side, even though that's how it's going to look like what's happening right here. Because in this case, the Ca and Cl2, the Ca is going to be, the formula is going to be CaCl2 on the side. Now, in this case right here, do you see how it's iron 2 oxide? Doesn't that mean that iron's an Fe2+ and oxide's an O2-? So if you have an Fe2+ and an O2- and you put them together, I'll help you out with it here. The end formula is going to be FeO. So can you do me a favor? If you have Fe plus O2 goes to FeO, can you balance that for me, please? I want all of you doing this, even though obviously I'm going to put this up on the screen in a second. Okay, I'm going to move forward. These are just a bunch of examples that we kind of can do later. So first step, you always have to write the formulas, and then you balance. Don't balance as you're trying to write the equation. Okay, the answers are written here. Take a look at the second one. That's the one that we were doing in the first one. Okay, decomposition. Decomposing is when you have something just break apart and one reactant falls into 2 or more elements. So if we have something like NaCl, it's going to break apart into its elements. Now notice here, NaCl, if you were to do a break line and go right and separate the 2 out, the puppet show that we're doing, remember, is the 2 fingers held together. When they break apart, they're going to form sodium and chlorine. It's only chloride when it's part of a compound. But notice here that isn't Cl part of Brinkelhoff? So the Cl actually has to be written as a Cl2. So it's a kind of a big deal when you separate out. Because over here, you're like, wait a second, but that's not balanced. That's fine, because after you separate the sodium and the chloride into sodium and chlorine, remember chloride part of a compound, chlorine when it's by itself, you then can put coefficients in front of things to balance them off. We're going to move forward here. We did this last class period, but if you take a look at the H2O, if we look at H2O and we're like, what would it break apart into? Well, isn't H2O made up of hydrogen and oxygen? So when it breaks apart, wouldn't it make sense that it breaks apart into hydrogen and oxygen? And here's the thing, aren't both hydrogen and oxygen part of Brinkelhoff, diatomic molecules? So that means that H2O is going to break apart into H2 and O2, and then our job is going to be to balance.
Oh, so y'all can see it.
Okay, watch. This is kind of important. We're going to give you a gift here, and can you write this on the board for me? Can you write NiCO3 on the board?
Wait, what?
No, we do
Right.
I mean, you can do
NiCO.
NiCl.
NiCO3.
NiCO3.
Dan wants to do it.
Wonderful. It's a bold move.
Part 4. NiCl.
I'm looking at the ceiling right now. I'm guessing that's.
Wait,
Ian, are you
wait,
switching over?
NiCO3.
Is Ian up there?
Yeah.
But I can't see his. I can't find his.
It's like his computer died.
My
So
computer died.
you can.
Okay, so you're gonna have to use her computer. So NiCO3. Can you write it more to the left here, so it's actually a little bit easier for the people on the screen to see?
Sorry, like
NiCO3
again.
Can you write the NiCO3 all the way over to the left-hand side here, and let's tilt the computer so it's kind of straight. Nice. And an arrow.
An arrow.
And an arrow. Yes.
Yeah, I never like that.
Write an arrow.
Oh, all right.
Okay. So watch. The first thing we have to do in any time you're dealing with a reaction is determine what type of reaction it is. And if we have a compound just sitting there, hold up 2 fingers like this by yourself. Okay. Put your fingers together. If you have a compound sitting by itself, the only thing we can do is break it apart. Now, typically when we break it apart, it's just going to break apart into 2 elements. Now, whenever we have a compound, like take a look at this, the formula NiCO3. Put your finger on the board here. NiCO3 does not break apart like we normally would think it would. Now, here's my gift to you. If you ever have a compound like this, that you can see, isn't it more than just two atoms together? It has an Ni, a C, and an O. If we have more than that, on the right-hand side, we will write what the other formula is. Can you write NiO on the other side, please?
Sorry, say it again. NiO1.
NiO. Ni, and
Sorry,
then the letter O.
Crazy.
NiO. Okay, so what'll happen is this. If you're ever given a more complex decomposition like that, we're going to show you what one of the products is. And then all you're going to do is you're going to subtract the NiO from the NiCO3 and write what's left over. So if you were to actually just do a math problem, don't we have one Ni and one O that we've pulled apart from the NiCO3? So what's left over? Well, wouldn't we have, so write plus next to the NiO. Wouldn't we have a C left over? Like if we just did a straight subtraction, if we subtracted Ni from Ni, the Ni is gone. If we subtracted one O from CO3, wouldn't that give us CO2? Can you write plus CO2 on the other side? So our gift to you is this. Whenever you see a complex, can you put your finger on the NiCO3? NiCO3, yeah. Whenever you see a complex looking compound like that, that's not just a regular two atoms and together we can just separate apart easily, we will always give you, can you put your finger on the NiO? We'll always give you, put your finger on the NiO. Can you not hear me, Ian? Okay, put your finger on the NiO. Is it cutting in and out?
Yeah.
Okay. We will always give you that NiO, and what you have to do is just subtract that from the original to see what your other product is. So let's do a couple examples here. I'm going to stop I'm going to go back to.
Do you need me to state the board?
No, right now, but in a minute I'll have you up. Okay, so we're going to go back to screen sharing.
You can.
Cool beans.
So take a look at the second example here, H2CO3. So just like we did up on the board, they're always going to give you, and they being us, we're always going to give you one of the pieces of the product. So if you take a look at this, you're like, oh man, how would I break that apart? Because there's three different things that are involved. So you will always give you this portion right here. So if I look at H2O, then my job is, what is that compared to the H2CO3? So I'm going to subtract H2O from the H2CO3. So if I subtract two H's, that's going to get rid of the H2. If I subtract one O, won't that get rid of one of the O's here? So wouldn't that give me plus CO2 right here? So that is a typical decomposition. Now, this is a new type of reaction. You might want to jot this down. I gave you my notes last class period. You have these with you, but a combustion is always composed of a compound that has carbon and hydrogen, and it reacts with oxygen. And the product is always going to be CO2 and H2O. Now, that seems very wordy. Let's give you an example. So, I do want you to write on the board here for me now.
I got it.
So before you do that, I want everyone to take a look. Here's what a combustion is. A combustion is always a hydrocarbon plus oxygen on the left-hand side. Now, there's no real puppet show that we can do to help you with that. So you're just going to have to recognize that every time that we have a hydrocarbon, that's any compound that has carbon and hydrogens, occasionally there'll be an oxygen attached on here as well. And you see it plus O2. And here's the cool thing. Is there's only one thing it will ever form. It'll always form CO2 plus H2O. Oh, on the board, right, CH4, O2, plus O2.
Oh.
You're using Carolyn's screen, right?
Yeah.
Okay. Can you set it up so we can actually see the board from the laptop? Because right now I'm seeing just there it is. Perfect. Okay. So I believe it wasn't CH. What was the first one? I think it was C4H10, but let me.
It's the first one?
First one is C4H10 plus O2. C4H10 plus O2. C4H10. So put a 4 subscript next to the carbon, and a 10 next to the hydrogen. Okay. So here's what you need to be aware of. Can you write combustion on the right-hand side? On the left-hand side, actually. On the left-hand side. Left-hand side. Combustion. So there's no puppet show to do for combustion. So I'm just going to show it to you right here. Anytime you have a hydrocarbon plus oxygen, you always, the only two things you will form ever, put an arrow and write H2O plus CO2. Arrow next to that.
But what?
H2O plus CO2. I'm like about 15 seconds from having Caroline come back up here, not because I don't love you to death, Ian, but this is taking a little bit longer. And Caroline was a rock star, everybody. Not necessarily an indictment on Ian, but more just a praise of how well you've been doing, Caroline. Okay, right, H2O plus CO2. Now, do me a favor. Can you underline the H2O and the CO2? Underline the H2O and the CO2. So I need all of you guys right now to understand, and this is what's super cool about this. Anytime, and then underline the O2. Underline the O2 on the left hand. No, sorry, the O2 on the left hand side. Okay, what she's underlined will be exactly the same for every single combustion. The only thing that will change, can you circle the C4H10? The only thing that will change with combustion reactions is that compound. That's the only thing that's going to be different. So, for example, right underneath that one, can you write C2H6 plus O2? Plus O2. And an arrow. So if I were you guys and I were looking at going, what the heck do I do with this? You're going to recognize that this is a combustion because all combustions are always a hydrocarbon plus oxygen. Now, that being the case, the only products ever are always going to be H2O plus CO2. So you can immediately just write those two products down. You write H2O plus CO2 down. Okay. Now, the easiest, this literally is the easiest reaction to write the overall reaction in because always, and can you underline C2H6 right here? Underline it. The only thing we're changing in our reactions is going to be that. That's it. The O2, the H2O, and the CO2 will always remain the same. What becomes challenging with these problems is balancing. Can I get a head bob here? So let's try one more. On the upper right-hand corner, can you write CH4 plus O2? Okay. Again, if you put your finger on the CH4 for a second. Okay, put your finger on the CH4. You're doing great. Okay, that CH4, that's a hydrocarbon. And we're putting it with oxygen. So the only two products you can possibly have are H2O and CO2. So just write H2O and CO2 on the right-hand side with an arrow. Okay. Now, let's look at this right here, and let's balance this one together. Is this a balanced equation? Can you look at the up top? And let's put a finger on the CH4 to start off with. Don't we have one carbon there? How many carbons do we have on the other side? Can you maybe shift the screen a little bit to the right? Okay. So everyone see, we have one carbon here. How many carbons do we have on the other side?
One.
We have one, so that's balanced. Put your finger on the H, H4. Don't I have 4 hydrogens here? How many hydrogens do I have on the other side? Two, right? So if I have 4 hydrogen on the left-hand side and 2 on the right-hand side, don't I have to put a coefficient of 2 in front of the H2O? So put a 2 in front of the H2O. Okay, now that's balanced off my carbon and my hydrogens. Now let's deal with my oxygens. And the oxygens are going to be a little more challenging here. How many oxygens do I have on the left-hand side? Don't I have 2? How many oxygens do I have on the right-hand side?
3.
Try again. So yeah, see, look at the 2. So you have 2 right there, agree? And then you have 1 oxygen there, but see that oxygen there, isn't it multiplied by 2? Put your finger on the 2 in front of H2O. 2 in, right there, and then put another finger on the O and the H2O. 1 finger on the 2, 1 finger on the O. That 2 is being multiplied by the O. So don't you follow here that I have 2 O's? What's that?
So you have 2 on both sides?
2 O's, and then you have 2 O's in the CO2 as well. So altogether, you have 4 oxygens on the right-hand side. Okay, pause. I need everyone to see how we get 4 oxygens on the right-hand side. Do me a favor. Put your one finger on the 2 in front of the H2O and one finger on the O. Another finger on the O and the H2O. Okay, so that 2 in front multiplies by the O. That means we have 2 O's in the H2O. Remember, we're trying to balance off our O's right now. Also, put your finger on the O2 and the CO2. Isn't there another 2 O's there? No. Leave. We're only doing the right-hand side. So on the right-hand side, can you write, put an arrow from the H2O, from the O and the H2O down and write 2? Arrow down. So write 2 oxygens. And then, okay, and then in the CO2, write an arrow down and write 2 oxygens. Does everyone see how we have 2 oxygens in the CO2? And then because the 2 is multiplying in front of the H2O, we have 2 oxygens there. So altogether, don't we have 4 oxygens on the right? Can you write 4 oxygens down there somewhere? Just write 4. So together, it equals 4. On the left-hand side, don't we have 2?
Mm-hmm.
So in order to balance that, wouldn't we have to put a coefficient of 2 in front of the O2?
Yes. Wait, but
So-
don't you
All we have right now, so up above, next to the O2, let's put a 2 in front of that. And that will get us a balanced equation. Are you with me? Okay. We'll come back to balancing in a second. Right now, I'm going to go back to the PowerPoint because there's one type of reaction that we haven't covered. So far, if you remember from last class period, we did synthesis, we did combustion. Or I'm sorry, we did synthesis and decomposition, and then we did double replacement. Remember, what's a double replacement of do-si-do, where we replaced our partners? Now we have combustion. There's one last one. And it's called a single replacement. So, can you do me a favor? Can you erase everything on the board? And let me show you what a single replacement is. I want you to write A plus BX.
what?
A as in, yeah, A as in abacus plus BX.
Wait, BS? Wait.
A is in abracadabra, and then plus BX. B as in boy, X is in xylophone. Is that an A? I can't tell. Okay, so I'm going to put it back on myself just for a second here, and everyone take a look just for a minute. So watch. Let me do the puppet shows we've seen so far. So this right here, where we have a single and a single, and it forms a compound, that's called a synthesis. So this right here, a single and a single, that's a synthesis. When we have a compound sitting there just by itself, and we're like, what do we do with this? We break it apart. That's called a decomposition. So if I have a compound, I break it apart, that's called a decomposition. Occasionally, the compound right here is going to be really complex, so we'll give you one of the products, and you'll have to subtract it from what you started with. The third thing we did last class period is we did a double replacement. A double replacement is essentially 2 compounds together, and the first thing stays together, stays in the same spot, and the back thing, these 2 right here, they just switch places. Now, the combustion, there's just no way for me to do a puppet show with that. But single replacement looks like this. You have a single thing and you have a compound. You all watching me here? So here's the idea. This single thing, it wants to break in and take the place of this first thing here. So let's pretend this single thing is Joe McFootball, and the first guy right here is Puny McScrawny. So if Mr. Football comes along, is all like, hey, how you doing? The partner right here, let's pretend these 2 are dancing, right? The partner right here is going to be like, ooh. And what will happen is that this guy will come in and take the place, knock off, and hook up with that. And then the other guy will end up sitting over here on the side by itself. So if you go and you look at the actual example on the board, we're going to go back to the board presentation. So that A, can you put a loopy arrow from the A to the B, underneath the B? So like a little loop arrow from the A to the B, and then put a loop arrow of the B going away. So like a B on the top, But yeah, put an arrow of the B like looping away, exactly like you did before. Just the opposite. Yeah, perfect. Yeah, perfect. And then write an arrow.
Oh, what?
Put an arrow next to the BX. Okay. So what a single replacement is where a single thing, put your finger on the A, comes in and knocks its similar element off. So let's say A is a positive ion, it's going to knock the positive ion off of the X. So that B gets knocked off. And what happens is the A takes the place of the B. So on the other side, can you write AX plus B plus B plus B? Okay. So just take a notice here. Do you see how in this reaction, you see how the A has just essentially bumped the B off of the X? Are you with me? Thumbs up if that makes sense. Okay, now watch. Here's the thing. Put your finger on the A, please. On the other side. On the other side. Okay, so that A is approaching a compound. And what that A wants to do is take the place of the B. The only way the A can take the place of the B is if it's stronger than the B is. If the A is weaker than the B, then the B is going to be like, get lost, and is not going to allow it to replace it. So how do we know whether or not the A can replace the B? So every time you see a single replacement reaction, you're going to see a single thing. So put your finger on the A, and you're going to see a compound. Put your finger on the BX. Okay. So the A is going to try and replace the B, always. The only way the A can replace the B is if the A is stronger. And the way we know that is there's going to be a table, and if the A is higher up on the table than the B, then it can replace it. So let's go to our notes right now. I'm going to go back to screen sharing, go back to the PowerPoint, and if you have your textbook, that'd be really, really great, and I would really encourage you to bring it to the next couple classes as well. Okay, so I'm through combustion, and we're going to talk about single replacement. So if you take an example of these right here, you see how the Na at the very bottom of the page here, the Na knocks the K off and takes the place of it with the Cl. And you see also how the F2 takes the place of the Cl and knocks it off. Now the question is, why didn't the F2 knock off the Li? Well, anytime you have a halogen by itself, halogens will only replace other halogens. Everything else will always replace the first thing. So let's get a couple examples. So let's take a look at the first example here. K plus ALN. Now, would you all agree that the K, since it's a metal, is going to try and replace the Al, which is another metal? And we're telling you that happens, so the K is going to take the place of Al. So in your minds, you're now going to have a K plus when it forms over here, reacting with an Al, reacting with an N. Okay, let's do this on the board together. So let's write K plus ALN. In fact, can you write both these examples right now? I'm going to leave this on the screen. Can you write these examples side by side, please, Caroline? Those two examples. You got it, Caroline? Caroline, can you hear me?
Yes.
Okay. Have you written those two side by side
Oh.
on the board?
Okay? Is that okay? Like one's underneath the other.
That's fine. I kind of wanted a little more space, but that'll work. Okay. No, that's fine. That's fine. That's fine. That's fine. Okay. So if we take a look at this, and let's look at the top one here. All right. Put your finger on the K. Okay. In almost every single case, the metal is going to try and replace the first thing in the compound. So if the K were to replace the Al, wouldn't the K now hook up with the N?
Yeah.
Now,
Oh, yeah.
watch this. So put the K, put the K, put like an arrow like you did up above with the K bumping off the AL. So underneath, swing the K in there and then have the AL get knocked out. What are you doing? That was perfect up there. What are you? So, sorry. So do it on the bottom. Just repeat exactly what you saw on the top there. So the K comes in on the bottom, knocks out the AL, and the AL gets kicked off. So let's put the AL get kicked off. So on the product side, can you write the AL on after the plus sign? Just write AL sitting there. So the AL gets kicked off. That means the K is going to hook up with the N. But now here's what's really important. You can't just write KN because K, whenever you write a compound, you have to balance the charges. So can you write K plus up above where you're writing there? So K plus, and can you write N3 minus? N3 minus. On top. Okay, so in case you're wondering here, the way I got the K plus and the N3 minus is from the periodic table. I looked up and K is in group 1 and nitrogen's in group 5. So I knew that nitrogen wanted to gain 3 electrons. That's why it forms a 3 minus. And I knew that potassium wanted to lose. So if I have K plus and an N3 minus, don't we do a crossover to get the formula? So what's my formula going to be? Wouldn't it be K3N?
Yeah.
So you see how the N, do a crossover right now for the 3 down to the K.
Where you want me to write it?
You can use the crossover right on top of where it's at. So draw the 3 going down to the K. Yep. And then underneath that, why don't you write K3N? Wonderful. So that's our actual single replacement reaction right there, K3N. Now, you may be saying, wait a second, how can there be 3 Ks when there's only 1 K on the other side? That's because whenever we're writing the new formulas, it doesn't matter what we had on the left-hand side. What we have to do now, though, is we have to balance. So do me a favor here. If you take a look, put your finger on the K on the left-hand side. How many Ks do we have there? Just 1, right? Don't we have 3 Ks on the right-hand side? So can't we put a 3 in front of it? Okay. Then we have ALN. Now, if you take a look at ALN, don't we have 1 AL on one side and 1 AL on the other side? And don't we have 1 N on one side and 1 N on the other side? So we're balanced. So we're good. Fair enough? So let's take a look at the second example, ZnCuCl. Same exact thing. Isn't the Zn going to try and replace the Cu? So on the other side, we'll have the Cu that's got kicked off. And now I have to write a compound between Zn and Cl. But in order to write that, we have to know what the charges are. So Zn's charge is a 2 plus. And Cl's charge is a minus. Cl's a minus. Okay. Can't we do a crossover? Cl2. Okay. Again, do you notice how it didn't matter how many Cl's we had on the left-hand side when we're writing the formula? But once we've written all the formulas correctly, now we go to balancing. So if you take a look at the ZnCl2, put your finger on the ZnCl2 on the right. On the right. Yeah. We always want to start with the most complex compound if we can. So let's look at the Zns. Don't we have 1 Zn here and 1 Zn on the other side? So they balance. And then don't I have 2 Cl's on this side? And how many Cl's do I have on the other side?
Oh,
Just 1. So you have to put a 2 in front of the CuCl. Oh, you guys jumped out of there quick. Hey, before you abandon me really quickly as well. Next class period, I'm going to have you guys do a practice with the ionic formula. Is the sub right there? Is the sub still in the room?
yeah. Yeah.
Take me to sub really quick. Hey, are you going to be covering my classes tomorrow as well?
Yes, all week.
Okay. Oh, wonderful. So, and I know that you're way more qualified than to just sit and babysit here. But tomorrow, what I'm going to be gone during their class period. So,
Right,
so what they did today, I gave them the ionic formula worksheets 2 and 3. You gave it to them. I had them work at the beginning of class on the ionic formula worksheet 2. Just for practice, let's have them work on the ionic formula worksheet 3. And to start off with, so give them about the 10 minutes. The answer key is in the is on the table to the left.
Right.
And then there's two overall worksheets that they're going to work on that deal with what we've been just doing in class right now. And those are the two that they're going to work on during class time. And there's a third worksheet that's going to be their homework.
And
Yep,
this
that one. Yes. Yes. So the one on the right hand side, that's going to be their homework. Because that's a
Right-hand
Poggle. It should be. So I'm doing it the wrong way. On your left hand side, that's a Poggle activity, and I think that's going to be their homework. But there should have been two worksheets like that. There should be another worksheet like the one on your right hand side. There should be another
Okay.
worksheet like that.
Okay.
Those are the two they're going to work on in class. The one on the left hand side, your left hand side, that's the one they're going to do as their homework, and if they finish the first two worksheets.
Okay.
That makes sense. Now, the previous class, the A2, I believe it is, on Thursday, the A2 class, they're going to be working on reaction sheets. That's my pre-AP Chem. They have an entire packet they're going to bring to class that has, like, I think 13 different worksheets in it. So I'm going to have them work through the first 6 so they can work however they want. I need to let Caroline go, but I'm going to see you in just a second in this next class. So I'll follow up if I need to. Thanks so much for helping me out, by the way. Caroline, thank you so much.
Thank you.
Just realized I was